Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're happy to have Fedya Nazarov from Michigan State University. The problem he'll tell us about is one I've been interested in for many years, and in particular I remember asking about it to Jean Bourgain, who thought about it, and others. So I was really delighted when Fedya made the breakthrough that he will tell us about.
Okay, should I go ahead? Okay, thank you for inviting me. Special thanks go, of course, to Yuval, who had extreme patience with me. And since in Microsoft it was announced the most mind-boggling title, I want to make a simple introduction about what it is. So it is how likely is Buffon needle to meet a Cantor set. So what's a Buffon needle? It's a very simple device. Here it is. So you put the center randomly in some bounded region on the plane and rotate it at random angle. So that's one experiment. That's another experiment. And you may say that it's very silly, right? And indeed it is, but you may modify this experiment a little bit. You may also introduce a set, a fixed set. And the question we want to ask is the following. You put your Buffon needle, you rotate it, and you ask whether it meets the set. You should think of it as extended infinitely in both directions. So in this case it does, in this case it does, in this case it doesn't, in this case it doesn't. So that's Buffon needle. Hope it's not mind-boggling anymore. Now the question is, what's the Cantor square? And the Cantor square is also a very simple construction. So there is some extra I'll put up later, but here is basically what it is. You take the unit square and you put squares of one. Oh gosh, that's what the difference is between the Microsoft projector and the usual projector. I should do it like this. So you take a corner square of size 1/4 of the original size and put 4 such corners squared. So the sum of side length is still 1. And then you do the same operation in each corner of the new square. And then you do it again and again and again, as many times as you wish. So the nth iteration Cantor square is Kn is the result of n such operations. K0 is just the unit square. K1 consists of 4 squares of side length 1/4. K2, which is drawn here, consists of 16 squares of side length 1/16, and so on. In general, we have 4 to the n squared of side length 1 over 4 to the n. And the question that we want to ask is how likely the Buffon needle is to meet the Cantor square. So what's the probability that a random line drawn through some finite region on the plane at random angle intersects one of those small squares, or maybe more than one, I don't know. And if you think of it a little bit, you realize that instead of rotating the line, you can rotate the square. So suppose that the line is all the time vertical, but the square is rotated by the random angle. It's going to be exactly the same model. If you think a little bit more, you realize that once the line is vertical and once you fix the angle at which the square is rotated, the probability is basically the projection, the length of the projection of the Cantor square to the line. Now I'll bring it up. So that's your projection. Actually, that's exactly 1/2 of it because of symmetry around the origin. I reserved this other half for something else. And the question is what the measure of this projection is relative to the measure of the projection of the region in which you throw your center. Roughly speaking, it's like that. So what does it mean? It means that the probability is actually the same up to some constant as the average projection of the Cantor square rotated by various angles to a horizontal line. And the question is, how does it behave as n goes to infinity? So, first of all, what was known for quite a long time? Well, it was known that it tends to 0. And the reason was the Bezikovich theorem. If you pass to the limiting set, which is Cantor dust, it's usually called Cantor dust, then this set is purely unrectifiable, and you can say that, and it has of course finite H1 Hausdorff measure because the sum of lengths is fixed all the time. So when you pass to the limit, you can cover it by squares with arbitrarily small, with fixed sum of lengths, but arbitrarily small size. So such sets necessarily have projection of measure 0 to almost every direction. There may be some exceptional directions, of course, but most of them will be 0. The question is, when you pass to the limit and use the dominated convergence theorem, you then say that the limit is 0. The question is, how fast does it tend to 0? And up to 2002, well, what was it? 2002 there was no estimate. And then Yuval and Boris came with an estimate. So what was the estimate? The estimate was this. Well, it's in the introduction, in the abstract, so you got it already. So it's e to the power minus logarithm star of n. Well, it's a wonderful estimate, except what's logarithm star, right? So logarithm star is the number of times you need to take log to get 1 from n. Well, so suppose you want to write down the number for which it is less than 1/10 in decimal notation. Well, the claim is that you will not have enough paper in the entire universe. So if you convert all stars, galaxies, whatever into paper and pencils, then you'll still run out of paper trying to write this number for which it is 1/10 over 10. Otherwise, it's a wonderful estimate. So the point was to improve upon it a little bit so that you would be able to write such n for, say, finite time, maybe for a lifetime, okay? That would be a great improvement. So, and Yuval came with this problem to Michigan, and we put our heads together. So he, myself, and Sasha Volberg, we discussed it for a while, and then we exchanged a few emails. So what we can currently get is that this average projection length does not exceed n to the power minus 1/6. Okay, actually it's even a little better than 1/6, but 1/6 is the best inverse integer we can get. So that is about the results. So now I am going to spend the rest of my time trying to present the proof. So any questions about the formulation so far? Yeah, I should mention the lower bound. So of course that's a nice upper bound, but how does it compare to the truth? Well, it's not hard to show, and it was shown by Matila in 1980, that the set has the average projection at least 1/n. So it's a simple L2 argument. I'll tell you what it is in a moment. You see there is one more character in this play, which is f, and I didn't tell you what it is yet. So the lower bound is 1/n. So how does the proof go? It consists basically of two parts, of the Fourier analytic part and of the combinatorial part. And I'll tell you the combinatorial part first. So now I want the screen, probably not right now, but in a few minutes I want it up. So right now I want to explain what that F2 is. And probably you can see it from the picture. It is just the sum of the characteristic functions of the projections of all small squares in Kn. So here you have just one square above this point, any points in this interval, namely this square, so the function is 1. Here you have nothing for a while. Then you come to this square, it jumps up to 1. And somewhere here you still have this square and also have this square, so it jumps to 2, then goes back to 1, and so on. And I tried to make it more or less realistic. Of course, it should be thought of as a symmetric function, so you should take this and mentally flip it to that side to get the full picture. But one half of it is enough. So it's some function which is fairly irregular. But what can you say about this function? Well, first of all, its support is exactly what we are looking for, right? It is the projection of the Cantor square to the line. So the size of the support is exactly what we are after. That's one thing. Secondly, its integral is always 1, or comparable to 1. Because you have 4 to the power n squareds, and each of them contributes 4 to the power minus n to the integral. Okay? And how can you show that the support is not small? So let me say a few words about how you prove the lower bound. Well, you can say that the support is at least as large as the integral of fn squared divided by the integral of fn squared. Okay? That is about 1, and it remains to estimate that. And that's a fairly easy exercise, because you cannot estimate it for any given theta, but you can estimate the average over theta. So if you take the expectation with respect to the angle, you get what? Always 1 here, but you can get the expectation here. Let's see, probably it would be right to put it just in the denominator as it is, or you can do the usual trick with taking half size of the set where it is small. So the point is that you have, roughly speaking, this inequality, at least more or less speaking. Maybe it's too exactly, probably it's too exactly. And this one is quite easy to compute, because it's just, you just look at all pairs of squares and look at which lines give you non-trivial scalar products between these things. So that is actually about n, and that's not hard. So the easy part is that it is about n at most. So that was essentially Mathieu's proof of the lower bound. I leave it to you as an exercise. So now comes the combinatorial part. And what's the combinatorial part? How do I turn it off for a while? Power. Okay, wonderful. And can I turn the lights on? Well, it's not yet. So what else should I do?
The microphone.
The switch. Where is the switch?
Just ask what you want.
Well, I want white and blackboard, actually whiteboard, without any violet spot on it. Or if you want one violet spot, we can proceed with a violet spot. So which way do you want it? It's okay, it's gone. Why? Fine. So here comes the combinatorial part. So fix some k. And assume that you want the measure of your projection to go below 1 over k. And take some very big capital N. Okay? So the question is, how long should you wait for this to happen? And I will not give you an optimal bound, by the way. I'll give you something like 1 over log of n instead of n to the power minus 1 over 6. n to the power minus 1 over 6 is a little bit more technically complicated. But how do you get, say, log or something like that? It would still be a great improvement. So, well, I claim that all you need to wait for is that you have k squares in Kn intersecting one vertical line. So I claim that if you find just k squares in Kn that have pretty much the same projection, then you'll not need to have to wait long after that to get the projection less than 1 over k. And why is it so? It's because of self-similarity. So suppose that at some moment, say at the moment n, say prime, you have that pile, that stack of k squares. You take this stack and forget about it. You can say that the projection of this stack is only 1 over k times the total side length of the squares in this stack. And now you have some other squares lying around. And let's go one n prime generations again in each of such squares. So if you go any number of generations in these squares, still you have not greater projection, right? So here you don't spoil anything. But here you also can find the pile, now a much smaller pile. In each square that is left. And that pile also collapses in the sense that the projection is much less than the total sum of side length. And so on. So suppose you have x steps. So let's go x times by n prime steps. What do you get then? Then you get one big stack, a lot of smaller stacks, a lot of smaller and smaller and smaller stacks. And the squares that are stacked at any point give you only 1 over k times their side length, their total side length. So the total side length is 1. So the squares that are stacked give you only about 1 over k. Well, maybe twice that, but who cares? How about the squares that are not stacked? How many are they? Well, after first generation, after first attempt to go n prime steps, you have 4 to the power n minus k of them. N prime minus k of them. And then, in each of them, you have the same number of bad squares. So if you go for x generations, you have this number to the power x, right? And what's the length of each projection now, after you go x and prime generation? It is 4 to the power minus n prime x. So what is that? It is just 1 over k plus 1 minus k divided by 4 to the power n prime to the power x. You want to make it less than 1 over k as well. So what does it mean? It means that x is greater than, let's say, 4 over n to the power n prime divided by k logarithm k will bring you below 1 over k here as well. So you lose one exponent if you do it this way. It's a very rough way to do it, but it's very simple to explain. That's why I chose it for the talk. Actually, of course, if you want n to the power minus 1 over 6, you cannot do it this way. You should do it in a more clever way. But even this tells you that once you achieve this picture, the time you need to wait to drop the measure of the projection below 1 over k is just exponent of this particular n. Okay, so the point is to estimate this n, for which it is true. Now, you should understand one thing here. This works for any angle. This combinatorial path works for any angle. Now, this n doesn't exist for every angle. So there is an angle where the projection is always of length 1 and the stacks are always of size 1. So what's that projection? You just take the projection to this direction. So it's easy to realize that those lines are parallel if you draw them accurately. So if you have a picture like this, the tangent is like 1/2, right? So if you look at the picture like this, you realize that no matter how many generations you take, your projection is the entire interval. So there are angles for which you'll never achieve this, and the stacks are always of height 1. So the point is that there are exceptional stacks. Okay, you have to live with exceptional stacks, and you say, okay, but we are going to show that they are of small measure angle-wise. So what would be enough? It would be enough to have the measure of exceptional theta also not greater than 1/k. So I want to show that outside a set of measure at most 1/k, so the measure of the set of exceptional theta, I have a stack of height k in a reasonable time. Once I do it, I'll get some estimate, some reasonable estimate. Okay. And that's the remaining part of the talk. So the remaining part of the talk actually works with Fourier analysis. And since Yuval told me that nobody here knows it, I decided to give you a short crash course. So now I want that thing again. So what kind of Fourier analysis? Come on. It's warming up, okay.
We have a 10-second break now.
Yeah, we have a 10-second break.
Ordinary projectors are like a bicycle. You get on and you ride.
Exactly, and that is like an airplane, so you should warm up the engine, go to the runway, take off, and only then you can fly.
But once you get going,
Well, I wouldn't say I go faster with this, right? Okay, so here is the crash course in Fourier analysis, and many people might think that Fourier analysis is something really complicated and high-tech stuff. I'm going to convince you that it is the simplest thing you can think of. So I'll need 3 inequalities, and here is the first one. Oops, how do you change it? You see, sometimes you have to navigate here. Put it here. No, I understand. I put it other way, but it won't fit. It fitted well before. So how do I change it to normal setting? Turn. Okay, wonderful. Thank you. And now I want to make the field a little bit bigger. Zoom, probably. Zoom out. And out is 3 hands or 1 hand? No, yes, it's 3 hands. Perfect. I'll probably even a little bit smaller. Okay, modern technology. So it's the first estimate I want to present. You get an arbitrary set of real numbers lambda k's that are just k capital, so you have finitely many of them. And then you want to estimate this integral from below. The integral is taken over the interval minus 1, 1, from which the small interval from minus delta to delta is dropped. And you need to estimate the square of that. How do you estimate it? Well, you introduce a function, a triangle kernel. And the only thing I want to know about the triangle kernel is that its Fourier transform is non-negative. Okay. How do you see that? You realize that it's a convolution of the interval with itself. So its Fourier transform is there. Fourier transform of an interval squared. I don't even want any formula here. So what happens if you integrate against g? Of course you get a smaller number, except you have that middle from minus delta to delta. And how much does that middle contribute? At most the length of the interval times the maximum of the function squared, right? Now, how to compute this? Well, if you open all parentheses, you get the sum of all g's of the differences, g hat of the differences. G hat of 0 is 1, because the integral is 1. So you get k terms equal 1, and some positive junk, which I just disregard. And that gives you this estimate. So that's the first thing in Fourier analysis I want. Okay, any questions about it? So you see, nothing to be scared of. Here is the second thing, also a very difficult theorem from Fourier analysis. You take a risk product, which is written above. It's just exactly what it is. The product of 1 plus cosine 4 to the power kx from 0 to some big number. I don't care what that number is. Then I claim that if you take a short interval of length less than 1, then the integral of the risk product over that interval does not exceed square root of that interval. Well, you can think that your interval is of length 2 pi over 4 to the power m without loss of generality. You can put any interval into an interval of this kind of comparable size. And then you just split your risk product into two. The product from 0 to m minus 1, the product from m to l. Now the first product is a product of m factors, neither of which exceeds 2. So it's 2 to the power m at most. But the second product is 2 pi over 4 to the power m periodic. So the integral over I is just 1 over 4 to the power m times the total integral. And the total integral is 1, because if you open all parentheses, if you put cosines as exponents and open all parentheses, you see that the only way to get 0 out of those exponents, plus minus 4 to the power m, is to have them all 0. So you need to use all ones in that product, so the total integral is 1, and of course r is non-negative. Cosine never exceeds, never is below minus 1, at least in mathematics. Okay, so it turns out that the integral does not exceed 2 to the m times the integral of r2, which is 2 to the m times 2 pi over 4 to the m, which is 2 pi over 2 to the m, which is exactly the square root of the length. So that's another difficult theorem from Fourier analysis I'm going to use. But now comes something really fancy, which is Salem trick. So I should explain you what it is. It will require more than 2 minutes. So suppose you have some set of exponents. I drew them as points on the line. So those are lambda j's. And suppose you have them in bunches. Lambda 1, lambda capital 1, lambda capital 2, lambda capital 3, and so on, lambda capital whatever. And suppose that you know that the cardinality of each bunch does not exceed k. But the distances between bunches are much, much bigger than k. Some big multiple of k, very big multiple of k. The point is to estimate, again, you take an interval minus delta delta, you drop it from the interval minus 1, 1. You take delta much less than 1 over k. And the point is to estimate the integral of the sum of the square of the sum of all exponents in your set. So how do you do it? Well, once you saw that first slide in Fourier analysis, you may imagine that I'm going to use some reasonable function g here to replace the integral over this by the integral of the entire line against g. And here is exactly g that should be used. Well, that can be used, let me put it this way. So what is it? Well, here is the exact graph. You can easily see it. And my point is that it can be made of triangles, of a few triangles, namely of 3 of them. One triangle that you saw already. One triangle like this of slightly higher, of slightly bigger height, roughly speaking height 2. It's 2 plus delta, something like that. And one triangle of height about 1 with base from minus delta to delta. So just imagine, you should get these break points, and that's exactly what your triangles do. Otherwise it's linear in between. So what can I say? I can say that the Fourier transform of G is, well, it's not positive anymore. If it were positive, I would be in a very good shape, but it's not too much negative, because the only negative contribution can come from here. This to give you something positive. And if you compute that Fourier transform or estimate it, now you'll probably have to use the formula, but it's not a big deal to compute the Fourier transform. You'll get this estimate. Because for the triangle you get, roughly speaking, decay like x squared. And this is just a rescaled estimate for the triangle that is shrinked several times, delta times. So now, once you have that function, you do it like this. Actually, there is a small mistake here. This should be 2 delta. Well, the marker is not very perfect, but I hope you'll see it. So, what is PL? Let's take the sum over each bunch and integrate G against the sum of PL squared. So what do you have? You have the sum of integrals of PL squared plus the sum of all pairwise products. And the sum of all pairwise products would integrate to this amount, G hat of lambda I minus lambda J, where I and J are in different bunches. So how about the first part? The first part we've seen it already, because delta is much less than 1 over the number of elements in each bunch. You can say that it is at least 1/2 times the number of elements in the bunch. So the total sum of the integrals here is at least 1/2 times the cardinality of lambda, the total number of lambdas you have there. How about the second one? Well, let's fix just one index I and let's sum over J. And what do you have? Well, this is not too much negative. So what I'm claiming is that you have not more than k such lambdas at distance d, then not more than k at distance 2d, and so on. Just consider all the neighboring bunches, the next bunches, and so on. And you'll get this sum, and this sum evaluates, roughly speaking, to z. Again, it's a simple exercise to check that this sum is pretty much the same as 1 over delta d, not greater than. And therefore, this sum is at least minus 1/4 for fixed I, the sum over all j. Now, what is the total contribution of that thing then? It is at least minus 1/4 times the cardinality of lambda. You subtract, you are still left with cardinality of lambda with some coefficient like 1/4. Okay, so any questions about the Fourier analytic part? I mean, not the Fourier analytic part, but about this crash course. So those are probably the most natural estimates you could think of if you really want to estimate the integral of the square of the sum of exponents. Okay, wonderful. So now I'll use all these estimates without any further notice, and again we have something like a break here. So now I'll do the rest on the blackboard. And can we put the lights on? That's the best you can do. Okay, wonderful.
Thank you.
It seems to me that that room has a brain of its own, though I know that the brain is behind the door actually, right? So here comes the Fourier analytic part. So we want to get a stack of k squares. And what does it mean in terms of Fn? Well, it means that the L infinity norm of Fn is at least k. Okay? And what's the bad thing about the L infinity norm? It's a very nice norm to compute, of course, but the problem is that you cannot do much Fourier analysis with the L infinity norms. So what is the convenient norm for Fourier analysis? Can anybody tell me? L2, exactly. So I'm going to strengthen it to this. And since the integral is 1, the integral of n is always 1, this actually implies z. So now, what's Fourier analysis? We are going to use Fourier transform somewhere, right? So the integral of fn squared is pretty much the same. It depends on how you denote fn hat. So it's not up to constant. It is the same as the integral over r of fn hat of y squared dy. Here I need an absolute value because that's positive, but this is whatever it is. Now the question is, what is fn hat? And what is fn? Well, fn can be written as a convolution, because the Cantor square can be thought of in the following way. You just take 4 perpendicular vectors of equal length, like that. Then you take, at each endpoint, you take 4 smaller perpendicular vectors in the same directions, 4 times smaller perpendicular vectors. Then at each point you get this, and so on. And then you put a square around each endpoint. So what does it mean in terms of fn? Well,
You're working with a fixed angle now?
yeah, I'm working with a fixed angle. So everything is for a fixed angle. And then we'll see how to average over angles in the end. Exactly, I'm working with a fixed angle. So now, what does it mean in terms of projection? Well, there are 2 vectors. One probably has a longer projection, and one has a shorter projection. And the longer projection is always comparable to 1. It's between 1 over square root of 2 and 1. So I'll normalize it to be exactly 1. But the shorter projection may be anything between 0 and 1 then. The vectors. The vectors are used in the construction of the Cantor square. So I have 1, t, minus t, and minus 1.
We're just looking at the 4 ones. Initial ones right now.
Yeah, I'm looking at the 4 initial ones, and then I use the same vectors, so but with coefficient 4 to the power minus 1, and then 4 to the power minus 2, and so on. And then in the end I also put a square here, which would mean that in the end I also put an interval of length 4 to the power minus n here. Okay? So what is fn then? Fn is then just the convolution of nu n with 4 to the power n times the characteristic function of, well, let's say minus 4 to the power minus n, 4 to the power minus n. To be completely correct, I should put some coefficient here, sine plus cosine of the angle, but I do not want to. Okay? It's a coefficient comparable to 1. And you'll see that we don't need much from this particular thing. Anyway, so what's nu n? Nu n is just the convolution from 0 to, I believe, n minus 1 of 1/4 delta minus 4 to the power minus k delta minus 4 to the power minus kt delta 4 to the power kt delta 4 to the power minus k, of course. It's such a convolution.
Why do you have the power 4, the 4 to the power n in the top row?
Because I want the characteristic function, not 1 over that. So the total integral should be 1. If I want the sum of characteristic functions, I should normalize so that the total of 1 norm is 1. Here it is definitely 1, and here I should normalize this to 1 as well. And then they will give exactly the sum of characteristic functions, not it with some coefficients. Okay, that's the easiest way to see it. It's because it's not a delta measure, but 1 over 4 to the power n delta measure. That's another explanation to it at each point.
Okay, so
If it were a delta measure, you would just have this, but this has this coefficient and that has this coefficient. Okay, and I want to split it like this. Okay, wonderful. So let's take a look at this one. Well, one obvious thing you can say is that it is at least the integral from 1 to 4 to the power n of f hat n y squared dy. A part is smaller than a whole. And then on this interval the Fourier transform of the convolution is of course the product of the Fourier transform, but on this particular interval I don't need to care about this one. It stays around 1 up to 4 to the power n. The first 0 is roughly speaking at pi times 4 to the power n. Okay. So this one disappears, and with some constant it is at least the integral from 1 to 4 to the power n of nGÇÖth n of y squared dy.
Times 8 to the n? Oh, no, time
no.
cancels, yeah.
Exactly as written. So now I'm going to assume that this doesn't happen. So assume that there is a big set, say E, such that, probably it's better to put it here, so E is the set of theta such that Fn squared integrates to at most k for all n not exceeding k. And also I can add to here that there are no stacks of height k, height. I believe it's correct. No, it's not. Okay, k up to n. Okay. Something is wrong, but
For all n less equal capital N, what?
for fixed capital K.
No, but the condition.
For all little n.
And capital N, yes, thank you. Capital N. Okay. So let's consider such a set, and I want to show that this is a small set. That outside this set, I definitely arrive at this. So what can I say for any point on that set? Well, I can say that this integral is at most k. So the integral from 1 to 4 to the power n, capital, for example, of nGÇÖth of y, I can use n here, squared dy doesn't exceed k. Now, I want to use it in the following way. I want to split this integral into about n divided by m, there will be one more parameter m, integrals between 4 to the power n minus m and 4 to the power m. Let's say sum of n divisible by m, integral from 4 to the power n minus m to 4 to the power n nu, I'll be lazy to write that n capital here anymore, squared doesn't exceed k. Okay. Now I can average it over 1 over e. So I can also average it over e, and my parameter will be t. T is pretty much the same as theta, it is tangent of theta minus pi over 4, so the derivative is bounded.
I don't understand this thing you just read down. N, little m is fixed?
N does not exceed n. Little m is fixed, yeah. Little m is fixed. So fix little m.
N just runs over multiples of little m.
Yeah.
Up to big N.
Up to big N. And I think that big N is really large, so it will be really larger than m. So there will be no problem with that.
That means that n is a multiple of m.
Yeah, that means that n is a multiple of m. So 3 dots. 3 dots means divisible. Okay? It's the same thing, right? Up to maybe the end. The end here is bigger, yeah. You just take them in bunches of m.
Thing is covered m times.
No, n is divisible by m.
Runs over multiples of m.
From 0 to m, from m to 2m, from 2m to 3m. That's how it goes. So there are, of course, n divided by m bunches here. So I'll average it over E. It won't change anything because it's pointwise on E. So I'll average this over E. It is the same number, so it's still correct. And then what do I say? I say that there exists some n, not exceeding n capital, such that the integral from 4 to the power n minus m to 4 to the power n nGÇÖth squared, actually it's average over E, is not greater than what? K times m divided by n capital. Okay? Now I'm going to do a thing Yuval hates. I'm going to say this. So since it is true on average, it's true for half of the points with 2 here, right? And then I'll assume that it's true everywhere on E, but by E now means that good half. It's still of the same measure, so the measure we didn't change. If we can estimate this new measure, we'll be able to estimate the old measure. So now I will erase this. Put 2 here and say everywhere on E. Okay? Well, that's one thing. Now comes the other thing, which is a pure computation using all the Fourier analytic stuff.
Wait, they exist in N and everywhere on E. So
Yeah.
depending on how you put the parentheses, this means different things.
It means this. I can find the set E of measure 1/2 of the previous one and Nn such that this holds.
Such that there is an N.
There was quantifiers or existing quantifiers, so there exists a set of half measure and there exists an n, so you can compute them in any way. Yeah, if there was existence quantifiers, it doesn't matter in which way you put them. It cannot mean different things.
It's for all t in.
But that holds for all t. For that fixed n, it holds for all t.
For all of t.
I fix n small from now on. From now on, I'll work only with that particular n small. So for all t in E, I had to change the t. Of course, I changed it depending on Zn, but who cares? For t in Zt, you have a pointwise inequality. This integral is not greater than this number. So what comes now? What comes now is the computation of nGÇÖth. And you know how to compute the... So here is new. So you know how to compute the Fourier transform of a Dirac mass, and the convolution just gives you the product. So basically you have integral from 4 to the power n minus m to 4 to the power n of cosine 4 to the power minus k, so product, a big product, from 1 to n, of cosine 4 to the power minus k y plus cosine 4 to the power minus k ty divided by 2 squared dy. That's what you have. You may say I'm cheating a little bit because, to be honest, I talked about nu n capital here, and here it is nu n small, right? That is written here. But there are other cosines in which the argument is very close to 0. Converges to 0 like a geometric progression beyond 4 to the n. So indeed you have to leave only n small factors here. You can easily change it to n capital, or other cosines are extremely close to 1. like a geometric progression. So I actually wrote this one, right? And now I'm trying to cheat you with this one, but it's the same. Okay, we wrote that down. And now we are going to estimate this product, this integral from below. How am I going to estimate this integral from below? Well, I'll split it. So the product without square, so product of cosine without square, I'll split it into P1 and P2, and I'll do pretty much the same trick as I did with the estimate for the risk product. So P1 will be the product from 1 to M, and P2 will be the product from M, say M minus 1 here, from M up to whatever N. Okay?
This is a different M?
Same M.
The same. Exactly the same M.
No K. So in the integral, Y runs from 4 to the, in the product, K runs from.
Oh, okay.
So okay. So it's going to be the same M. You can do two different parameters here, but it turns out that the best thing you can do in the end is to put them equal. So that's why I put them equal from the very beginning. So of course those are unrelated parameters physically, meaning of them is different, but it turns out that the best thing you can get is when you put them equal. Okay, now I'll start with P2. Okay, and I also want to make a change of variable. So I want to make a change of variable y to 4 to the power n y. And then my integral is 4 to the power n, which comes from the differential, times the integral from 4 to the power m to 1, and then the product is going to be of cosine of 4 to the power k, not 4 to the power minus k, and k still runs from 1 to n small, right? Just this change of variable, and then actually I want to split in this setting. So here k runs from 1 to m minus 1, and here k runs from m to n. So I'm looking at this.
K on the right is n minus k for the.
Yeah, n minus k on the left, exactly. So now I'm trying to estimate the integral of P2 squared. And the integral of P2 squared I'll estimate in the following way. It's the integral from 4 to the power minus m to 1. Well, it's symmetric, so in principle I can take a symmetric interval as well. It's 1/2 of the integral over minus 1, 1 minus this short interval here. And if I open all parentheses and represent cosines as exponents, what shall I have? Well, I shall have the following thing. I shall have, of course, 4 to the power number of factors, because you have 4 in the denominator when you put exponents here. So 4 to the power m minus n. Then you have it squared, because you square. And then you have the integral of the sum of exponents. What was that, y? Let's call it y. Okay. And what can you say about your exponents? You can say about them a very nice thing. You remember that there is no pile of, or no stack of height at least k. What does it mean in terms of your exponents? Because these exponents are still the same things as projections of centers of the Cantor squares, but in the generation n minus m. And you have no pile. Now the typical size, since you start from m, the typical size now is 4 to the power m, that used to be 1. Right? So you can say that if you take any interval of length 4 to the m, there are no more than k exponents there. Okay? That's perfectly well. So how do you switch to that bunches stuff? Well, you can say that if you have k exponents with distances not much greater than k between them, you have k exponents in the interval of length k squared, right? So if 4 to the power m is much bigger than k squared, you can say the following. Start with any exponent, go by k, or something, a big multiple of k, if possible, find the next exponent, go again. You'll be able to do it not more than k times. And then there will be a gap of size much bigger than k. So if for m is much bigger than k squared, that would mean that your exponents go exactly like on that picture I presented, in bunches of k with distances much greater than k between them. And what did we know from that picture presented? Well, we knew that it is at least 4 to the power times the number of exponents up to an absolute constant. So this integral is at least 4 to the power n minus m, with some small constant like 1/4. So the total integral is at least 4 to the power m minus n. And remember that it's multiplied by 4 to the power n. And m is, roughly speaking, logarithm of k. Okay? That's all you need. You may say that you also need 4 to the power m be less than 1 over k, but it's automatic with this inequality. That would be the second restriction, it's weaker.
The last line. But yeah, the bottom line on the right.
Yeah.
No, on the right.
Yeah.
The bottom line maybe.
Yeah, this one makes sense to keep. So if it were just P2, you would come to a contradiction immediately, right? Because if you compare this with 4 to the power m minus n times 4 to the power n, what do you see? You see that actually this is much bigger than that, right? So if there were no P1, you would come to a contradiction already. But P2 is okay for any angle, and you remember that there are exceptional angles. So what's so exceptional about them? The exceptional thing is that the integral of P2 is actually killed by P1. Now how do you proceed with P1? Well, you proceed in the following way. You look at P1 of y, and it's the same thing as written here, except you put 4 to the k there, and you write the sum of cosines as the product of cosines. So what do you get? Sum of cosines is twice the product of cosines, so P1 is basically the product of cosines of 2 to the power minus k minus 1 times 4 to the power k y plus ty, some angle, cosine 2 to the power minus 1, 4 to the power k, y minus ty, difference angle. That's just elementary trigonometry. And you want to say that this thing is not very small. So how to estimate it from below? It seems like an ugly product. But if you think a little bit, you realize that you have one nice formula from probably should go back to your school year to find this formula, but here it is. And you also should multiply by twice 4 to the power m. That is just sine of 4 to the power m u. Sine of the double angle, many times. So what does it mean? It means that it is at least 4 4 to the power minus 2m, well, I don't care much about this particular 2 here, times sine of y plus ty, sine of, so if I want the absolute value of it, okay.
What happened to the 4 to the m?
4 to the power minus 2m, right?
No. I mean, not that.
This one is the same as this one. And half sum is product of cosines. Sum of cosines is twice the product of cosines. So
But the sign, inside the argument of the sign, there is a 4.
yeah, 4 to the m, yes, thank you.
At the beginning, isn't that just 4 to the minus 1m?
Where is the beginning? So here is the formula I'm going to use for y plus ty and for y minus ty. Okay? So here there are all numbers that we need. So this one, 8, and so on, the last one. But plenty of other numbers less than 1. And that will give you sign. So if you drop those numbers less than 1, you'll get an inequality. So that's the thing.
How did you get the 4 to the minus 1?
Because 4 to the power m comes from here, this product,
Oh, and also the other.
and 4 to the power minus m comes from this product. So I put it on the right. So I just put it on the right. Now what's the danger? The danger is that the integral of p2 squared, which is 4 to the power m minus n, you remember. So that's another line I want to keep. Is something that is actually concentrated at the points where those signs are small. And where the signs are small, we know that set. This is just a set of intervals of length 4 to the power minus m times epsilon. So take epsilon and consider the intervals. This is a bad set. And I'll call this set omega. And that set depends on t. It is the set of y. So omega is the set of y. And actually this set depends on t. Now, what I want to say is that it may of course happen that integral of p2 squared over omega is large. Actually, it's the entire integral here. But I want to say that on average, the integral over omega is not too large, if epsilon is very small. So that's the very last line that I'm going to use, maybe the last but one. So it goes like this. I'll take the average over E, integral with respect to t, and then I'll take the integral of over omega, it depends on epsilon, of p squared, okay, p2 squared dy, and I'll try to estimate it. So how shall I estimate it? Well, you see that if you take p2 squared, it can also be written as a similar product. Only k will be running from m to n. And then when you take the cosine squared, is 1 plus cosine of double angles, plus cosine of double angle. So actually p2 squared, let me put it here. is the product of 1 plus cosine 4 to the power k y plus ty divided by 2, product of 1 plus cosine 4 to the power k y minus ty divided by 2. Right? From m to n, from m to n. Okay. Neither less nor more. Wonderful. What can I say now about the average? Of course, what I'm going to do is the following. I look at y plus ty. So suppose that y plus ty is in that interval. And I'll denote z by u and z by v. And the integral over e I'll replace over the full integral from 0 to say 2 pi or 1. T runs from 0 to 1. So let's look at this integral. Once I make this change of variable, I have u and v basically independent, running between 0 and 1. What's the determinant? Well, we may say that the determinant really vanishes when y is what? When y is close to 0, right? Because the determinant is y. But remember that I integrate actually P2 not from 0 to 1, but only from 4 to the power minus m to 1. So the determinant is at most 4 to the power m. That's the worst case that may happen with the determinant. And then I have my integrals. So one integral is over this set that I'll denote, say, I epsilon. So this set will be denoted by I epsilon of this risk product 1 plus cosine 4 to the power k u divided by 2. And the second integral will be taken just from 0 to 1. And now I'm in a very good shape because I have a 4 pi over 4m periodic function. So now I'm going to use the estimate for the risk product I did before. Expect it is shrink 4 to the power m times. So what's going to happen if you shrink it 4 to the power m times? Well, it's going to happen that this guy will be, of course, 2 to the power m minus n square root of epsilon. And this guy will be just 2 to the power m minus n. And also I have 1 over e, and 1 over e I assume that e is big, of measure at least 1 over k. So 1 over e gives me at most k. So what happens on average over e? What happens on average over e that you get k times 4 to the power m, which is k squared, times 4 to the power m minus n, which is something you compare it to, times square root of epsilon. So if epsilon is like k to the power minus 7, which is quite possible, I can choose any epsilon I want, I can say that the integral of P2 squared, at least at one point, over this exceptional set omega is much less than 4 to the power m minus n. So the integral over the good set, where P1 is large, is at least 4 to the power m minus n. And now comes really the next line. So the integral of P, which is P1 times P2, is at least the integral of P2 squared over the good set times, so how small is P1? 4 to the power minus 2m from that sign thing times that epsilon, and epsilon is k to the power minus 7, And of course I have to square it, because it's squared here. And that is at least, what is it? K to the power minus 10, I believe, right? 11 from, no, not 10. 14, 18, 17. Times 4 to the power minus n. And you remember that the integral of fn squared actually had a factor 4 to the power n in front of it because of this change of variable. So 4 to the power n cancels out. And I can say that in E, if it is of big size, there is at least one point where this integral is at least k to the power minus 17. M, let me remind you, is about logarithm k. Now, if this is less than z, I'm done. And that's a very reasonable estimate, like k to the power 18 for n. So what is actually proved is 1 over logarithm of n to the power 1 over 18. And that's the end of the story. I overstepped my time by about 5 minutes, but I hope you'll forgive it. So Ival wanted to comment a little bit on motivation for those who are interested in the end, so if he wants to do it.
Okay. Anyone who wants motivation?
So, any questions? Of course, the last part was technical, but it was unavoidable. I mean, I tried to present the entire proof. And the one thing I wanted to convince you about is that the proof is fairly simple. So it doesn't really involve too much.
Not even worth writing up.
Well, we finally decided that it's worth writing up. Once we came to n to the power minus 1/6, we decided that. While we had 1 over log, we decided that. Maybe, maybe not, but n to the power minus 1 over 6, you all convinced me that it's worth writing up. So we are going to publish it. Okay, so basically.
In hindsight, it don't look like the first thing you would do.
Not the first. I mean, the point is to switch to the Fourier transform. Once you switch to the Fourier transform, those are the most standard estimates you can think of. So if you open Zygmunt's book and look a little bit, you will not find exactly this, but you find there are a lot of things in similar spirit. I just singled out 3 inequalities I needed, but I mean, if you read through Zygmunt's book, those inequalities would be as natural to you as ABC.
Basically, the combinatorial factor, you choose just the right 3 inequalities of Zygmunt's book.
Yeah. Well, you need to choose 3, so it's just a cubic problem.
Cubic in a rather large n.
Yeah, cubic with a rather large n, yeah. But basically it's fairly straightforward, and this is
Thanks, Peres.